Okay, so this is an introduction to how the EECS 200 online labs work. So first you go to this website up here to bring up the introduction page, which shows links for each of the labs. I'll go to lab 2, the one on motors. This shows the lab write-up that tells students what is expected for this lab and how to do it, along with questions at the end. And this is basically exactly the same as what the in-person students get, except for a introductory video as to how to use the online system, and a link right here that is used to go to the actual simulator on the web server. So I'll click that. Notice it brings up another tab. So the old tab is still here with the write-up, so the student can go between these different tabs to do the lab and to remember what it is they're supposed to be doing. So as you can see here, there's a whole bunch of different lab equipment that is programmed up to work for this thing. So each of these pieces of equipment is basically exactly the same as what's in the actual in-person lab. So here's a power supply, function generator, multimeter, and way over to the right here we have an oscilloscope. So each one of these works similarly to how the actual instruments work. There are some buttons that don't work because we don't need them for the lab, so I haven't implemented them. But as you can see, you can turn on the oscilloscope, you can get the trace of what's going on. You turn on the voltmeter. In this case it's set up to be a voltmeter to start, but you can change it to an ohm meter or a capacitance meter as needed. The function generator up here you can also turn on, and it shows, in this case, a sine wave. You can use square wave and other types of signals. I'll turn these off because we don't need them for now. The only one we're really going to need is the power supply for this lab, and it has an on-off switch as well, and allows you to program what kind of voltages and currents you want. And it's 3 channels. We're only going to be using one of them. Below that is a breadboard. So the breadboard has also these banana sockets, and it has a create button here, which allows you to create components that you put on the breadboard, like resistors and wires, and in this case a motor. Next to that, over here to the right, we have a button that allows us to create cables. So for example, a banana to banana cable to connect up the power from the power supply to the banana sockets on the breadboard, so that we can power our devices, whatever they happen to be. So for now, what we really want to do is create a motor and hook it up to the power supply. So we'll go over here and we'll hit create. It allows us to choose what we want to create. So we'll pick motor, ignore the name, and hit create. It creates this little teeny motor here to the right of the create button, and it's got these 2 black circles along the other 2 ends of it. Those represent the 2 connections to the motor, right? It has 2 wires to connect it up, and we use these circles to grab that connection and drag it to the breadboard like this. And you get it close to one of the sockets on the breadboard, it'll snap into place. Move it to a different one over here, snaps into place, and note the motor got bigger. So the further apart those 2 circles are, the bigger the image of the motor gets. And the one thing about this motor is that it has this flap attached to the shaft, which is supposed to represent a piece of masking tape that one has taped to the shaft in order to allow us to see the motion of the shaft as the motor turns, and to count and get a speed for the motor as a function of the different voltages we apply. Okay, so we've got the motor. Now we know we need to hook it up to the power supply somehow. Power supply only has banana sockets, so we need a banana cable to connect to the other banana sockets on the breadboard, and so we need wires to connect up from these breadboard sockets to the breadboard banana sockets, like that. So there's the red wire. We can do a black wire as well. Hook up to ground. Hook up to ground. And hook up to the other side of the motor. Okay, we're almost there. Now we need to hook it up to the power supply. And that has to be a banana-to-banana cable. Cables are over here to the right. And we can hook up banana-to-banana cable. Let's make this one red. We're going to hook up to channel 2, because that's what the lab recommends. And we can hook up another banana-to-banana. Let's make this one black. These for the other end of the power supply. Okay. Now we still don't have any power, so now we need to turn on the power supply. Still no power. Until we hit this button here, there won't be any power to channel 2. But we should hit this button first at the top middle, so that we can set what the voltage and current should be for this particular channel. We can punch it in, we can dial it if we want. I'm just going to type it, so hit 5, hit enter, that's 5 volts. Let's see. Now let's make it 2 volts. Hit 2, hit enter. Okay, we've got 2 volts. You can see over here it shows you that the setting is for 2 volts. Now if we hit the current button over here, see it shows us that we're setting the current now. And notice it's 0.1 amps already. So when we hit this button here, this is the dial for setting the current. And when you punch it once, it actually increments in 0.1 increments. So that got us our 0.1 and we're done. Still not on. We still have to turn the power on by hitting this button here in the middle. So let's do that and we'll see what happens. Okay, first off, you'll heard that beeping, buzzing noise, and that's the buzzing that the motor makes when it's on. And the motor makes a different buzzing noise depending on how fast it's going. Slower it's a lower tone, faster it's a higher tone. And so that part is a realistic attempt to make it just like in the real lab. Now the other thing you'll notice is the motor here, the flap is moving, it's turning, and the students use that turning of the flap. They count for maybe 10 seconds how many, and they get an estimate of how many revolutions per minute the motor is going. And then they figure out if the input voltage is linear with respect to that output, or non-linear, or some other function. Get a feeling for how that motor works. And that is the end of that particular lab. So I will turn that off. And now we can go back and we can look at a different lab. Let's say lab 5. This one's on distance ranging, which is basically how to use a ultrasonic sensor module that you can buy for about $10. And it has a requirement for some kind of power, 5 volts voltage, a little bit in current, and then it has some control input and output signals. So the display looks pretty much the same as it always did, except further down you'll see a ultrasonic sensor module here that looks pretty similar to the real one. It has 4 pins that we need to connect up. Top one is VCC, second one's trig, third one's echo, the fourth one's ground. Also note there's a ruler that I've attached to this so that it's very easy for the online student to measure the distance from this ultrasonic sensor. And so they hit create here, this button, and it creates an obstruction, let's call it, some object that has some position. And this front face here has a position in centimeters, so here we are at 8 centimeters away from this sensor, and you can drag it around and change how far away it is from that sensor. Okay, so what else do we have? We also have this Arduino interface further down. This is meant to be a representation of the Arduino IDE that one runs on your host computer in order to program and test the Arduino. And this right here is a USB socket, which is what you use to power the Arduino with while you're doing that. So part of the Arduino interface is a serial port. This is output from your code that is running on the Arduino. And right now, of course, there isn't anything running, so there's nothing showing on the serial port. There's also a code part here, which shows the code that you either uploaded or programmed yourself to put on the Arduino. And in our case, it's a simple test program that runs some code that we downloaded to run the sonars. And it's a fairly simple piece of code that sets up which pin is trigger, which pin is echo, and it then initializes the new ping code that runs the sonar, and then it goes into a loop which calls sonar.ping_cm to get a single reading from the sonar and print it. So it has these 3 print statements to the serial port. Now note we had the begin, so the baud rate, or bits per second, is 115,200, and that has to be the same as what we use up here, the serial port. So I've set them to be the same. In the in-person version, you can mess with these and get garbage to your serial port output, so I decided that was pointless. I don't really care about that, so it's just set to be what it needs to be. Okay, so to make this lab work, we have to put an Arduino on our breadboard, hook it up to our sensor, hook it up to our computer, and hence power it, and then everything should start working. Very similar to what we would do in the real lab. The only difference is that in person you actually have to download the code to the Arduino before it actually does anything. Okay, so let's create an Arduino. Look, it has a single black circle for us to move it around. And basically, once we've moved it around, let's move it down a little bit. It has a USB port here for connecting to this USB port over here. And then it's got all these pins, a zillion pins. So let's look at these pins. We'll zoom in using our browser, and we'll try to read these pins. About as hard to do in the browser as it is in real life. And you'll see it's got, these are all labeled upside down, and these are all labeled right side up. So you'll notice this is D12, this is D11. Why do I point those out? Because in our program, we said that the trigger pin was going to be 12 and the echo pin was going to be 11. So those are the digital in and out for the trigger and the echo functions of our sensor. And up here, if we look and we read upside down, this is V in, this is ground, this is RST, whatever that is, this is 5 volts. So the 5 volts is what we care about, as well as the ground. Those are going to be connected to our sensor as well. So 5 volts, ground, D12, D11, and the USB connector here. That's all that we have to connect up. And we'll connect this last, because we shouldn't be connecting up all these other things with it powered. Okay, so let's zoom out again, and we will create some cables. So in order to attach our sensor to this, we use something called a jumper socket pin. And if you look at one of these, I screwed up, let's try that again. Jumper socket to pin. Create. So let's do a red one. So this would be for, say, VCC. So this is kind of a hole that fits over this pin. This is a pin that fits into one of these breadboard sockets. So we grab that one and we drag it over to the end of the VCC pin. You'll note that it snaps into place into the center of that pin, which is what we want, so that we know that it actually made the connection. Then we go over to here, we put it onto the 5-volt pin, which is right there. Alright, so we'll make another one. Let's make this one black, and it'll be the ground. Drag him to the ground pin on the sensor. And we'll drag this to the ground socket of the Arduino. And another one. We'll make him green. Which is the trigger pin. Let's remind ourselves, the trigger pin is supposed to attach to D12. Right? So let's attach him to D12, which is right there. One more. Jumper socket to pin. Orange. Connect him up to this last pin. Snap, so we missed. There we go. It's the echo pin of our sensor. Connect him up to D11. Okay. Now, still, if you zoom out, you'll notice that the serial port still is blank because, of course, Arduino hasn't been powered yet. So last but not least, we need to power the Arduino, and that's with a USB-A to USB Mini B cable. So here's the A part, which is this flat kind of connector over here. So we'll drag it to the corner and it should snap to the middle, which it does. And then we'll take this one, and now you'll notice the USB connector over here has been kind of obscured by our cabling. We just have to kind of know where it is, and as long as we get close, it'll snap to the right place. And the moment it's connected, the lights turn on and start blinking, and the serial port starts printing information about what it thinks the distance is. And if we move down and drag this thing closer, we go to 6, you see that it starts showing 5 and 6. You'll note there's some error involved. Drag it back to 10, it's doing 10. So we can see that it's more or less doing what it should be doing, which is fantastic. Okay, so one last thing we would like to do with this particular lab is to see the signals that are on the echo and the trig pins on our sensor so that we can better understand how this sensor is working. So in order to do that, we need to do some wiring. So let's remove power from our Arduino before we do that. So let's just move this up a little bit. Note the lights go out, so it's not working anymore. And so we would like to connect D11 and D12 to our oscilloscope. So let's do that. We need some wires. Oops, in the wrong place. First we need some wires. Connect that up. So let's do a wire, a red wire. Let's see. Green, orange, gray. Let's do green. And we can see that the green one is D12. So let's have him go to VB, which is also green, just to keep things neat. Attach him there. So you'll see that just like a real breadboard, all these sockets in the same column are connected to each other electrically, of course. And these are connected to each other, but not to these. These are two different sets of connections. So those are connected to each other into the D12 pin of the Arduino. And then let's do another wire. We'll make it orange. And connect him up to VC. He's near enough to orange. And down here at D11. Okay. Now we still don't have it connected up to the oscilloscope, so let's go out a little bit. And now we can see the connections for the oscilloscope, and in our case we need to attach to channel 1 and channel 2 in order to have this work. But it can be any old ones, right? So we will do BNC to banana, which allows us to attach BNC at one end to the oscilloscope, these two bananas to these banana sockets here on the breadboard. So let's grab BNC first, push him over to channel 1. Okay. Grab the red guy, have him go to VC. Guy, we can go to ground, and do it again for channel 2. BNC to banana, create, drag him to channel 2 of the oscilloscope. You can see it's getting a little slow, something I need to work on. Attach him to VB. The other one and have him go to ground. Okay, and if we turn on the oscilloscope, we'll see, oh dear, there's nothing there. And then we realize, okay, the things aren't turned on, so we need to turn it on. Okay, so now the Arduino's on. That's still not showing anything. Oh yeah, we forgot to connect ground. So notice that there is some ability of the sensor to the system interface to notice if you've connected things up correctly, because I've got Spice running in the background to see how things are connected. If it's not connected right, then it doesn't show what you would expect. And it basically shows nothing in this case because we don't have ground connected. So we need to connect ground. So this end should go to ground, and I'm sorry, all these things are piling up on top of each other. You just kind of have to know that it's right there. And then this other end goes to the ground on the Arduino. And all of a sudden, the oscilloscope turns on with signals that you can see. Top one in green being the trigger pulse, which is a very short pulse telling the sensor to send out an acoustic signal. And then the yellow trace, which is basically a pulse that is called echo, and it turns on the moment the trigger is sent and turns off the moment a response is sensed from some obstruction. And so the length of this pulse is related to the time it takes for the signal to go out, hit the obstruction, and come back again. And so it's related to that distance. So let's just test that out. If we drag this obstruction to say 15 instead of 10, it should get much wider. Drag it to 20, it'll get even wider. And so the students measure that pulse width and convert it into distance to see if they think they understand how that pulse width is converted into distance. Okay, you can zoom in on this to see the numbers. You know, it's got voltage for the vertical volts per division, and it's got 500 microseconds here for time per division here. So you can, just like with any other oscilloscope, you can figure out what these distances are and use that for your analysis. And so that's the end of showing how the circuit simulator can work with these two examples. Now I'm going to show you how one of the robot simulators works. So let's go to Lab 3. Lab 3 is all about figuring out how to use the motors to make the thing move the way you want, make that robot move. And in our case, it is the first time they try to move the robot. And that means basically that they are doing it open loop. So all they have right now, there's a program that we wrote that is running in the simulator, and it's parameterized by these two numbers: the time that the motor should be on for going straight, and the time that the motor should be on for turning. And the idea is that we want to go make a square for the motion of the robot. It should go forward, right, then right, then right, and basically back to where it started. And the idea is the students need to come up with the right numbers here to make that happen. What I don't tell them is that this is pretty much impossible to do open loop, because the motors have various inconsistencies. So no motor is the same as the other motor, and they vary a little bit in time as well. And so when you tell them both motors to do the same thing, they don't do the same thing. And so the robot turns, because all we have is two wheels. So the robot will then turn a little bit, and it will turn a different little bit every time, because things are different every time. And so we implement this with some random number generators, so that they can see what's really going on in the simulator, and they get the same appreciation for how bad this is, both in person and online. So here we go. It's printing out the XY position of the robot as it moves, and you'll see that it's not doing real well. Of course, I haven't optimized those numbers either, but it doesn't do a real good job of going in a square. And this is actually the lesson of the lab for the students, is that open loop control does not work. And so they can save the results for further analysis, and they can rerun it to see it again, and it'll be with different random numbers, and then they can quit. So so that's one of the earlier labs. One of the later labs allows them to write their own code, submit it to the simulator, and then the simulator runs the code for them. So they have to submit a zip file. For example, I'll submit one of mine. This is code that is supposed to look for an orange water bottle and then move towards it until it gets close enough, and then it takes a picture. So this is using the camera on there. So it starts in some random direction and distance from this orange water bottle, and then they are supposed to first look for it and then move towards it. And again, it spews where it thinks it is and some indication of its state, if it can find something that's orange, and as it rotates around, it's still looking for something that's orange. Blob not detected. Finally it notices it. It moves towards it. It looks and sees how big the orange water bottle is in its field of view. If it's not big enough, then it recenters and moves forward a little bit, and it just keeps doing that till it gets close enough. And then it saves the image of the water bottle to a JPEG for further analysis. And there's other things that they do in some of the other labs. These are just examples of simple things that we have them do. So that is the quick overview of how these simulators work. Thank you very much.